Okay, so we just finished part A, and now we're on to part B. So part A told us that the flux through the volume, coming through the surface. So the flux that passing through the surface of the volume is equal to the flux change within the volume. So we found the first part, and we found out that A is equal to pi over 3. So now we're going to solve the right-hand side of the equation. So I have a couple of base equations up here that I just want to point out. I have a pre-solved equation for this del operator dot A. In the PDF attached to this video, if you look in the description, there's a general cheat sheet with these vectors and the del operators. For the sake of time, it's a little easier to use this dot product and then plug in the magnitude of our vector into the directions and then simplify that way. So we're going to do that for this video. The second part, this is a general expression for dV for a sphere. You can have dV for any shapes. It's just a differential volume. So essentially what that means is if I integrate just straight dV, I'm going to get the volume of whatever shape that I'm interested in. If I integrate ds, I'm going to get the surface area of whatever shape that I'm interested in. So we use these in our expressions because sometimes, this vector may be dependent on some of those directional changes that exist within the differential volume. So the volume dimensions affect our final result for these questions. That's why we need the differential volumes and the differential shapes. Okay, so let's go ahead and get started for this problem. Okay, so for step 1, what we're going to do is we're going to do this del dot d first, and then we're going to do multiply it by dv and find our integral bounds. So that's sort of our order of operations for this. So for our first part, for our del dot v, we're using this general expression, and we have, this is our d given to us by the problem. So I just copied and pasted that from up there. So we have a magnitude only in the r hat direction. So if this is like our general spherical vector, we just have this. We don't have a theta magnitude and we don't have a phi magnitude, okay? So this A is just any vector, represents any vector, so we can plug in our d values here. This is just representative of a vector in the expression. Okay, so we have AR, but we don't have a phi magnitude, so we won't need this piece, and we don't have a theta magnitude, sorry, and then we don't have a phi magnitude, so we won't need this piece. So we're only evaluating the first part of this expression. So our del dot A is going to be equal to 1 over r squared times the partial derivative with respect to r of r squared times the magnitude of the r hat component. So that is cosine squared phi divided by r cubed. So equals 1 over r squared partial with respect to r, and we're going to simplify our math over here. So we have 1 over r times cosine squared phi. Okay, so because this is the partial with respect to r, we are only taking the derivative with respect to r. Anything that's not the variable that we care about, we treat it as a constant. So for example, if I do the partial with respect to x of 3xyz, I'm going to end up with 3yz. Okay, so interested in the variable that we care about. Okay, so I have 1 over r squared multiplied by the partial with respect to r, and the partial with respect to 1 over r just becomes, actually I'll rewrite it. So 1 over r squared, and then it's going to be 1 over r squared times cosine squared of phi. So this is just the derivative with respect to r over here. This piece becomes r squared. So we're going to end up with 1 over r cubed. Sorry, not cubed. R to the 4th. R to the 4th times cosine of phi. Okay, so we have this first piece here. So we're going to take that and we're plugging it into our second piece. So this is just our del dot d. So we're solving and simplifying that before we integrate. Okay, so 1 over r to the 4th. So we're plugging in this piece here, plugging in this del dot d. So 1 over r to the 4th multiplied by cosine squared phi. And then our dv r squared sine of theta dr d theta d phi. Okay, so we're going to group our r squared terms. So we're going to end up with 1 over r squared times cosine squared phi sine of theta dr d theta d phi. Okay, next what we're going to do is we're going to group our like terms. So we have differential dr d phi, d theta, oops, d theta d phi. Okay, that's right. All right, and so we're going to group our like terms. So we're going to group all of our theta terms with one integral that has bounds. We're going to group all of our phi terms with one integral that has bounds, and all of our r terms. So let's go ahead and do that. 1 over r squared dr, and then we have cosine squared phi d phi, and then we have sine of theta d theta. Yeah, just double checking here. So sine of theta d theta over r squared dr. We just make sure that we actually get all of our terms. Cosine squared phi d phi. Okay, that looks good. So let's go ahead and find our bounds. So we need our bounds for phi, our bounds for theta, and our bounds for r. So r, we're going to go from 2 to 3 for r. Two to 3 for r, and then for phi here, we're going from 0 to 2 pi. So by convention, phi for a full sphere, 0 to 2 pi on this plane here, which like would be the xy plane, 0 to 2 pi. And then this theta is going to go from 0 to pi. Just by convention, that's the range. If we go all the way to 2 pi, it actually will double our volume. So just by convention, it's 0 to pi. You can actually try that one for yourself if you want to see sort of why that is the way it is. But for now, you'll just have to take my word for it. 0 to pi, 0 to 2 pi. Okay, so let's go ahead and evaluate these. So the integral of 1 over r squared turns into negative 1 over r. So from 2 to 3 multiplied by, we're going to use the this integral table here, just for the sake of time for this. Ooh. We're going to use it to solve our cosine squared. It'll save us a little bit of time here. You can feel free to use an integral table if you would like. So phi is our variable that we care about, so we're plugging in phi in for our x here. This is what we're trying to solve, and this is our solution for the integral. Minus, and in a previous video I actually showed the full steps to do this, but again it's a little tedious, so we're just trying to kind of go through the problem solving and not get stuck on number crunching here. So integral of sine of theta is negative cosine of theta here. Oh, cosine of theta, not phi. 0 to pi. Okay, so let's go ahead and simplify and solve this out. So we're going to end up with a negative 1 over 2 minus a negative 1 over 3, okay, times, so we're going to plug in our top bounds first, so our top bounds for these guys, and then we're going to subtract our bottom bounds. So 1/2 times 2 pi minus 1/4 sine of 4 pi, yeah, 4 pi, and then, oh, take away that bracket just for now, minus 1/2 times 0 minus 1/4 sine of 0, and then multiplied by negative cosine of pi minus a negative cosine of 0. Okay, so that's going to give us, so this is negative 1. So negative 1 minus a negative 1, because cosine of 0 equals 1. So it's going to be 1 plus 1, which is 2. Okay, so a lot of terms from here are going to cancel out because this sine of 0 is equal to 0. This is obviously equal to 0. Sine of 4 pi is equal to 0. So our terms that are going to survive here will have, so negative 1/2 plus 1/3 times, so 1/2 times 2 pi, we're going to just do pi, and then we're going to bring this guy all the way over, and then multiply it by 2. Okay, so now we're going to give these guys the same denominator so we can combine the fractions here. So we're going to do 3 over 3, so it's just 1, multiplied by negative 1/2. So we're just multiplying each fraction by 1, essentially. 2 over 2 times 1 over 3. to give them the same denominator. So negative 3/6 plus 2/6, and still also multiplied by pi, multiplied by 2. So we're going to end up with negative 1/6, and then multiplied by pi, multiplied by 2, and the answer is just equal to negative pi over 3. So, all right, so we found negative pi over 3 to be the answer for our right-hand side, and that was also the answer for our left-hand side. So in this problem, we also proved the divergence theorem for this sphere, but in the course of answering A and B. So we found out that the flux through the surface is equal to the flux change in the volume.